So I'll ask you to say something about synthetic differential geometry. So what I'll do is not much. There's no original research. It's just I'm going to do some survey, what it's about, and but I'll do it in such a way that we get links to synthetic algebraic geometry to try to highlight that aspect of the theory more than maybe the other presentations will do. So in that sense, but I don't know what it's about the presentation. So we can start by listing some axioms. So you start in a local ring, call it R. So far, so similar. But then you add a strict order compatible with the ring operations, such that X is invertible if and only if X is positive or negative. What you can also do is you can add that it's Euclidean. So this means that the positive numbers have positive square roots. You can take. You could also add a weak version of the order, but it's not going to be antisymmetric. So we can have a pre-order less than or equal to that is compatible. Not so this all out is to take forever, but we don't have. So you have the infinitesimals will be greater than or equal to less than or equal to 0. It's not antisymmetric. Then you can add that it's Archimedean. And there are some models where this would not be the case, but often it is. So this says that R is a natural number n greater than x. Okay. You can do more. You could say that it's formally real. So this says when invertible, then the sum of the squares is invertible. Let me put more emphasis here. Stay forward. To the Pythagorean. So it says that if you have this, the sum of the squares is invertible, then you have a square root. So I think if you combine formally real plus Euclidean, you basically get this. So sum of squares is invertible, then x is y squares. So this is taking lengths in long diagonals in rectangular parallel pivots. like you do in the Pythagorean theorem. Okay, so now, so far it's about the extraction of roots. Then there's the Coq-Levier axiom, which will look familiar. So if you have W is an R Ray algebra, then the evaluation map to our spectrum W, this is the equivalence. Okay, so this gives you your tangent spaces, the partial derivatives, and so on. Then there's the integration axiom. So this says that if you have a function in the unit interval, then you have a unique antiderivative that's 0 at 0. So we have the derivative by Coq-Levier, and just P prime is left, and P at 0 is that's unique such that we have this. This is how far you can do just in type theory language. But a lot of work uses more than just using some kind of modal type theory. Then you can have modal axioms.
And what about other differential equations? Then there's just the G prime equals F.
Yeah, I think you can do a lot from this. I'm not familiar with the whole breadth of work. There's been a lot of work since Hannes Koch and Villaweir and Edward Dubuc. Others. I think you can solve a lot of differential equations from these axioms. You build things up.
Yeah. Okay. I mean the other. Yeah.
I'm sorry. I have to say I don't know exactly what's the best thing you can do, but I'm sure you can do quite a lot from this as I recall. I just did not my usual will try to present things. Honestly, but there might be some mistakes. Let's see. So what are some modal things you can do? Well, one is that the beta of the Algebraic algebras are tiny. And this is part of the definition. So if you're thinking of this semantically, this is a smooth topos. Smooth topos is something where you have the first part of this, so you have a local ring with the Coq-Levier axiom, and you have this part, but this is extended externally. But to internalize it, you would have to extend the type theory. And this reasonably, you could do this in type theory, using the type theory with the Wiley. So as of last year, start to formalize things using this assumption. So the tininess means that exponentiating by W has right adjoint. Externally, and then, but it's not going to be a parameterized right adjoint, so you have to modalize it a bit.
So, sorry, can you give a simple example of Venn algebra? Maybe.
Yeah. Okay. Venn algebra. So something of the form R tensor. Let's see. I has the property that X to the alpha I multi-index size bigger than S for some S. So you have some number of generators, you have some integer S, and any product of more than S of the generators is 0, is in the ideal. So for the dual numbers. Okay, so that's one of these modal axioms. And then, I guess here I could say this is this product. Build here. Now, I'll mention some things to do with fiber. So you can have cohesion. This means that you have modalities. Okay, flat chart. So this is underlying discrete thing, and this is underlying co-discrete thing. Discrete, co-discrete, and this is called shape. So this would be the if you do this in the higher topos, this will give you the but now all of the previous things now we go to hot to make this useful, although it has precursors in the Beer. I don't actually remember. I think this shape is much more useful. If you do this in one category theory, it's going to be the set of connected components. So it's a kind of shape of a smooth space, but it's not as useful as having the infinity groupoid, the underlying infinity groupoid of the type one topos. But this is much better behaved if you get an infinity groupoid out. Yeah, but you can in fact extend this to differential cohesion, which Felix talked much more about, and I won't say much more about today. So you can extend these modalities. So which way does it go? Everything that is, you include the shape modality into the infinitesimal shape, which is I, and then it has a left adjoint, which is infinitesimal reduction. Then you include the discrete things in a modality for that's called infinitesimal flat. I don't know. I don't have a very good intuition for what is this. As I said, this is some further extension that could be very useful for working with synthetic differential geometry. So one could wonder what happens with the internal Dedekind real numbers. So the Dedekind reals are inside your model will be Archimedean local ring. If you will have a map from your R to the Dedekind reals, kind of evaluates a smooth real as an actual real number, and I think you would have a map from the underlying discrete thing. So you have, because this is because flat is a idempotent comonad, just a co-unit, and I think this factors to this R object. So if you have something that depends on on anything, you wouldn't be able to expect to get. The property you want is that all the functions, the endo functions on R will be smooth. That's not going to be the case for the Dedekind real algebra. You can, with the max, min, all kinds of continuous for non-smooth things. So but I think you should have this. So this is
What is B
flat.
No. What is BR and not the blackboard R, but our
flat of this one.
yes.
Well, there's going to be a co-unit in that, but I don't. It's probably the same as this. Should have the same in the good models. It'll be the same as the discrete real numbers. Yeah, okay. It's probably. Okay, so now let's talk about the range of models for this. And to get towards the models, I want to talk about Fermat rings, or Fermat theories, rather. So we'll spend some time talking about Fermat theories, which include commutative rings. So that's why there's a connection to synthetic algebraic geometry. So what's the definition? And I guess a reference for this would be the paper by Eduardo and Anas. It's called something like C infinity rings and Fermat theories. So the definition is that an algebraic theory T that extends commutative ring. I'm just going to this is as in algebraic geometry. Usually we just think about the commutative ring. So as an extension of commutative rings, this is Fermat if what? So okay, in so you have an extension of the theory of rings. So I'm going to write the objects, the representing objects, as something like there's an underlying ring, which is the constants of the theory. So let's see. From this you have K. This is going to be a ring because you have an extension of the theory of rings. So you have the constants will be a ring, and every model will be an algebra of this ring. So you have a ring of constants, and any T algebra T is a K algebra. Okay, so now we can think of but I'm writing these curly braces to mean this is now the free T algebra in n+1 generators, 1 plus n generators. So this thing is the free T algebra in okay. But what it really is to have an n+1 area operation in the theory, right? So, but okay, it's convenient to think of it like this. Any operation for any operation in n+1 variables, there exists a unique operation G in 2 plus n variables such that f of x plus y and then the z is equal to f of x and the z. So the z's are just parameters. So we really pay attention to what happens to the, we want to express a function in x plus y as, well, think of y as being small or like an epsilon, and I want to approximate that by f of x. It's like this plus y times g of x, y, and z. That's a terminology. So we have these things. And what you get is that as a ring, you have a lot of regular elements now. So the variable x in k of x is going to be regular. So if you think of the variable y in k of xy, that's definitely going to be regular by uniqueness. And then there is an embedding of k of xy, k of x into k of xy. That gives you all the variables of the regular elements. So that's useful. Another thing you can do is you can iterate this Fermat principle. So it's, I guess, it's really a kind of Adamar lemma, but I think the observation goes back to Fermat, and that's in some form, maybe not so rigorously, and then let's call it Fermat theory. Maybe it would be more historically just to call it Adamar theories, but there we are. So yeah, you can iterate this to get better versions of Adamar's lemma. So you can get, you can do it in all the variables. So for instance, if you have f in x1 like xn, then there exists, but no longer unique, not unique, gi's in k of the x's and the y's, such that you can write f of x1 plus y1 plus x and plus y, it's f of x lists plus some I, yi, g of x's and y's. Okay, so iterate this. And then you can do one better. You can now iterate this again to get the really good version, which I have. And you have n variable and n variable operation, and you have some s, and you want to get some higher, you get the value, and then you get something in terms here. But if you want to actually define the partial derivatives in this way, you want to iterate, and then you get uniqueness again. So, so if you have this, then there exists unique g's, g alphas, and they will take common variables, just the x's, I guess. And so this is for multi-indices of size less than or equal to s. And then non-unique h beta, but I need both the x's and y's, such that with a bit of abuse of notation, x plus y, meaning the same thing as up there, is all the partial derivatives up to order s, y to the alpha, g alpha of x's plus higher order terms, non-uniquely determined beta is 1, if they what I'm why did it be that, of course. So you iterate these expansions and then you get uniqueness from the uniqueness part of the first part and once you high enough. Okay. Let me erase the axioms, that's okay. Right, so what can we use, what can we do with these Fermat theories? And so the one thing is you can do quotients by ideals in the usual range fashion. So that's an important property. It looks like commutative algebra. So if B is a T algebra, and I is an ideal in ring sense, the only thing that makes sense, right? It's an ideal of the underlying ring, T or K algebra. Then we get a congruence. This implies A equivalent to B defined by B minus A is pi. This defines a T congruence. Let's prove that. So suppose we have an operation in variables, and we know that AI is related to BI for I. And now I want to show that f of the A's is related to f of the B's. But we can do that by the, so this means that B minus A is I. So what do we get? We get f of the B's is equal to f of the A's plus these differences. So this is equal to I guess we just use the first part of the second corollary, that is the first order part here. So we know that this sum here is f of the A's plus I have I terms sum over I, with I minus K I, and some G I, and evaluated at the A's, the B's. Okay, but these are an I, and I is an ideal, and this is an I, so that's good. So this means that we have good, we have very well understand. So this means that is a T algebra, and it's going to have the universal property, of course, the quotient. I haven't told you any examples of Fermat theories, except commutative rings. Commutative rings, you have this because you have it for polynomials, right? An example, the main example, But maybe there are others. I guess there are others. Just haven't really thought about it. Except for the two extremes. So you can take T to be determined by the Cartesian spaces inside smooth manifolds. So the Cartesian spaces are the ends. And so you can define an algebraic theory by a Labire theory. So the operations of R and N are the smooth maps from Rn to R. And this will be a theory. And yeah, so then just to remind you how that works, then T algebras in some finite product category E are the same as finite product functors in the Cartesian space. This and it's useful that you can compute limits of T algebras and filtered co-limits object-wise. So limits, filtered co-limits object-wise. But you also have all co-limits. You have all co-limits, but they're just not computed object-wise. In particular, you have co-products. And they'll be written as a tensor B. So for a general, let's see, in this particular case, we've called tensor infinity, maybe to distinguish it. So one notation is to call this infinity, so this is the full product. So it's just something you just have it by the universal property, but you don't compute it in a very nice way as a finite product functor. You just have to bash it out. So how can we do a comparison? So in general, you could do this trick. This will for any like algebraic theory. You can compute the limits and the fields of the co-limits object-wise, and we have co-products. So in general, do a comparison. You have three algebras, A, B. Three algebras, then you can form the, because they're also K algebras, where K is the underlying region of the theory T. You can form the tensor product in K algebras, and that's going to map into A tensor B. Yeah, that's about what you can say about that. So coming back to regularity, I won't prove this, but it is in fact, so now you can make sense of something like a freely adjoined, a generator would be this this tensor, not the K tensor product, but with the curly brace, so the free T algebra on one generator. So here, there, X is regular. Do that sort of similar ways. Do that here. All right.
But the A tensor B is generated by the image of.
Yeah, it's generated by the.
Yeah. Okay, those were the relations.
Yeah. Well, yeah, generated as a T algebra.
Yeah.
Okay. Yeah, so we would like to have some more T algebras than the thing to get from commutative algebra. So what you can do is you can put a unique T algebra structure on every Ray algebra. let's see how that goes. That uses the more fancy version of Adam's lemma. So if W is a Bay algebra, and B is a T algebra, then there's a unique T algebra structure on W extending the K algebra structure, such that from the conclusion map, on not just on W, but on B tensor W. So that's why I mentioned the B. You could take B to be BK itself, and then you would get W here. So W itself would also be T algebra. In fact, a W tensor any T algebra is going to be a T algebra in a unique way, and uniqueness with respect to the inclusion of B into B tensor W. So to T, this map is a T homomorphism. Actually, so I guess I should say, first, you only define this as a map into the algebra tensor product, but then it would then follow, once we prove this, then the algebra tensor product comparison will be an equivalence. Once you know that you have this result, once this is already a T algebra, then by the universal property, the comparison will be an equivalence. And two, for if C is any other T algebra, we have that the homomorphisms are the same either way. So columns of K from CW are the same as columns in T from CW, and columns over K from WC are the same as columns in T from WC. The other part. Okay, I guess I will prove this on this board over here. Yeah, this one here for the moment. We'll use that. Okay, so let's prove one, just of time. All right, so how are we going to get this unique T algebra structure? Let's first try to see if we can define the action of the T operations. And then if we figure out a unique expression for it, then we know that we can also use that as a definition of the T algebra structure. So suppose you have a W, and so W can then be written as, in terms of K modules, as K plus W prime as a modulus with product of more than S elements of W prime. That's part of by Bayes algebra. And then we use this version of Adam's lemma. So what do we want to do? So we want to say, so if F is an operation of parity n, and we have, so you have some elements J of J of A, I, B, I. These are elements in B tensor W, which I now write as B plus B tensor W prime. So we are going to get the inclusions of the elements of B, and then we're going to get some. B is not maybe a good name for this variable. We just call them y-axis. Y-axis. So we can write some elements in the center product. These sums where product of more than s of the y's will be 0. Okay. Okay, so now we want to know what should f of these guys be. So now j of the a's plus y's. Okay. I want to know what this is. Well, I just use literally this form up there. So it's going to be the sum multi indices up to s, y to the alpha, to the alpha of the first part, the j of the a's, plus multi indices as s plus 1, y to beta, and then beta is y's, but by the assumption this is 0, and we require that J is a homomorphism of T algebra. So these G's are operations in T. So we can flip this around. Y alpha J of G alpha of the A's. Okay, and so this is both uniqueness, and it gives an expression that allows us to determine, write down the T algebra structure. So that's interesting time. So we know we have some T algebra structures on J algebras. In the case of C infinity rings, mention that for T equals C infinity ring, power series rings. These have a canonical C infinity ring structure. And it's going to be isomorphic to the smooth tensor product matrix 1 to n of the one variable power series. So that's going to help with doing some power series manipulations. Yeah, so let's stick to the realm of C infinity rings, because now I want to get to these well-adapted models of synthetic differential geometry.
So what does it mean power series in one variable? I mean, we have a C infinity ring. So does it mean that I have any C infinity function I have to be able to plug in power series now?
You have to, if you have a smooth function,
Yeah.
And then you have you can plug in power series, and evaluate. I don't know the proof of this. I think, I don't know. I learned this from a paper on C infinity schemes by Joyce. And I can't vouch for how it's done. But I hope it's correct. It was published.
Okay, my question is about convergence.
Yeah. Well, you have to get the only thing you get back is a power series.
Yeah.
And I guess what you do is you just, it only depends, when you apply a smooth function, it only depends on, maybe it only depends on the tables. I don't know. It's a good question. I was a little curious about this, but I didn't have time to chase it up. There's something that's puzzling me a little bit about it as well. Yeah, so some other things you can do in the C infinity ring case, if you have a manifold, and you have a point, then you can get then the germs of functions around P, which is P. So these are germs of 0, 0 near P. This has the universal property in C infinity rings of being localization for all F such that F is 0. Another fact about this theory. Well, this one is a fact. Hopefully, this one's a fact, and hopefully, this one is also a fact. I mean, this one is, I'm pretty sure, because this is the whole thing that makes the well-adapted model story go through. You have a map from on algebra. The infinity function M. Equivalence E maps to So this is sometimes called Milner's exercise. Yeah, so what use is that? So the corollary of Milner's exercise is that when you take this rings of smooth functions, and yeah, so when this happens already with R algebra maps, it also happens with T algebra maps, but T being C infinity rings. So we get a functor manifolds to yeah, I guess C infinity ring actually, yeah, sort of. But now let's skip the finite presentation up. So this is fully faithful. So how do you get this finite presentation? We do this from the Whitney embedding theorem. Because M embeds into an open in some Rn with a retraction. So retract. So then it's a retract of something that's finitely generated, so it's finitely present. And this preserves terminal objects, transversal pullbacks, and open blocks. So in particular, since it preserves open covers, and in fact, it's sort of equivalent, I think, maybe this is due to Schreier, that preserving open covers, it's enough to preserve this one and yeah, this one. The interval from minus n to n, cover the real line, you preserve this and preserve this, or even this gives you that the in the internal languages be local and Archimedean. So this should suggest that we get, by taking sheet models on the side given by C infinity rings of planar presentation of with some kind of open cover topology, you're going to get these well-adapted models that includes all smooth manifolds. Okay, so now flip back to my chart. Bestiary models.
Well adapted means what you just wrote down there, that
Yeah.
yeah.
Okay, so we have a diagram. So if you look, L is by definition this category of loci. Yeah, it's loci, and with the C infinity ring of finally generated. Okay, and this has a bunch of subcategories. So here's the diagram from, there's a nice book on models of smooth infinitesimal analysis by Ulrik and Reyes. So you have this one at it's the largest one they consider. Then we have the finally presented ones, which they call LFP. Okay, that makes that should be self-explanatory. Then there's the Carrier side here, which sits in here, but has a right adjoint as well. And so C is objects of the form C infinity M tensor W by. Then this sits into something called the G, and these are the germ determined. So let's say these are the form C infinity M I, where I is germ determined, meaning F is I if the germ of F near P is in the corresponding restriction IP or P in the vanishing locus of I. You can test whether a function, a smooth function on M is in I by looking at the germs. Germ determinant. Okay. This one doesn't have a right adjoint, but there's an inclusion here. This sits inside there, and this has a right adjoint. Then there are the closed ideals. This is closed, obviously. And then what was E? I forgot to write down what E was. There's another restriction you can make. It will all be closed, and that has a right adjoint. Then there is something called the C infinity radical ideals, where you can test whether you're an ideal by testing a power. Maybe maybe near the vanishing locus, something like that. So this is something to do with radical, infinity radical. Then there is, oh, I just forgot what that really was, forgot to write it down. And then there's some sub-objects of those which are countably presented, countably generated. So these are like lots of sites that have been studied. So these are countably generated. And E sits inside this. And of course, you could go there. This is the diagram that's in what I can raise. And then just let me put some of the topics down. So if you take all the loci, so for each of the sites, we can pick a topology. So let's say we take the open cover topology, or we could take the finite open covers, maybe plus projections. For most of them, it doesn't matter. And then, of course, you have a co-discrete, only isomers. So most of these are very well behaved. The determined one, this thing actually. Take all open covers on the German determined C infinity rings. You get this curly G, which is often called the Ulrik topos. And if you take the loci finitely presented, you get a class. We know the theory, at least externally. So this classifies local Archimedean C infinity rings. This is the classifying topos for theory we know well. Then there's this Caille side, and then you get this curly C. This is the Caille topos. And there are many other lines. Then you get some inclusions. So you get inclusions here, inclusions there. I think you have this inclusion has retract as a geometric morphism to the Caille topos. If you restrict to, so it sort of makes sense that if you have all open covers, you get local and Archimedean. If you restrict to finite covers, you no longer Archimedean, so you just as a local C infinity ring. And of course, if you don't have any covers, then you just classify. That's sort of topologically finally presented C infinity rings pre-sheaves on that classifies C infinity rings. Yeah, and then these are sometimes called something like G fin. Doesn't matter whether you take projections. This could be called C fin. Yeah. Called B and this D. I think this is called like this. It's just a smooth Zariski. Okay, that's about as much as I had time to prepare for. But I think so. The thing that if you want to compare, so Urs often works with this Caille topos. Has a nice relation to the classifying topos for local Archimedean C infinity rings, which sits inside this topos as well. So might be interested in all of these. Mainly this is color letting. A lot of interest in these three there. Okay, thanks for your attention.
Yeah, so one thing about the power series ring, we can read it as follows. We just take our polynomials, so Rx modulo x to the n, which is a Weil algebra. And there we get a T structure by what you proved before.
Oh yes.
And then we take the limit And this actually works for every T algebra, not only for infinity rings.
Yeah.
May not look as a set as power series, but it would be the right power series of an object.
Oh, in that case, yeah.
Yeah. So
That's the way to how to understand it. Very good point.
Yeah.
Okay, one more comment to this. You can also the power series ring is the ring of smooth functions modulo ideal of all functions which have vanishing derivative.
Yeah, that's right. Yeah, that's
you can use this. Well, it's not there anymore, but this is
yeah, that's right.
also the C infinity ring by an ideal.
Yeah.
Yeah, and I try to I mean at one point when you define the higher derivatives, you say you just iterate.
Yeah.
And now when I tried, I would put instead of just using one y, I would use y1 plus y2. Do this twice, and at some point I have to put them again together. But then I think some 2's appear in the formula. So do we need characteristic 0 here or not? I mean, you didn't state it, but I'm not clear how to get rid of the 2's appearing.
Yeah, and it could very well be that I was giving something that had a standing assumption that 2 was invertible.
No, well, actually, any natural.
Yeah, that's a Q algebra. Yeah, it could be that you want to be Q algebras. Okay, could well be. I missed that maybe. Yeah, thanks.
Yeah, okay, or maybe that's a different proof. But
you could check it. I mean, the proof in Anders Fox's book is very syntactic, and check it out.
Okay.
Any other remarks, complaints?
One thing I wonder is when you do synthetic differential geometry, do you have a replacement for the risky local choice?
It would be hard to internalize, but if you have to take into account somehow arbitrary covers of given by arbitrary finitely presented infinity rings. Yeah, I don't know if a good way to internalize that. It's a good
Yeah, when you have finite localizations, I guess.
Yeah, for the finite, it would be easier for these ones. It would be more manageable. But somehow I think this point by Schreier that the n-index ones suffice might give you a way out. Also, yeah. So, but on the other hand, if you work in these here, where you don't have the Archimedean axiom, what you do in synthetic differential geometry is you just take the natural numbers that sit inside R and call them the smooth natural numbers, and you work with those instead. Most of the time, you could do something with that.
Yeah, I mean, I remember David Jasmeyer's telling me that there's at least some version of local Zariski choice which is very restricted and used somewhere in the literature. He called it a secret axiom, SDG. And I think it works with the metric topology, but I forgot how it's phrased exactly. But the natural generalization to something like the risky choice looks like you have countable covers given by open balls. And maybe this just works. I think nobody has really checked.
Yeah. You want to talk about the excursion?
Yes. Let's think. Yes. So I think the weather